All right, so in a redox reaction, the number of electrons that are lost by the reducing agent has to equal the number of electrons that are gained by the species that's being reduced, or the oxidizing agent. Okay, so oxidation and reduction always go together, and for a redox reaction to occur, there has to always be a species that accepts the electrons and always a species that donates the electrons. Okay, and sometimes that's difficult to see. We did some pretty easy problems where we said something like iron plus 3 combining with zinc, for example, and we said if zinc was oxidized like this and iron becomes reduced, right? It's kind of easy to look at these elements and see which has been oxidized and which has been reduced. However, there are other kinds of chemical reaction or redox reactions. This is one of them. CH4 plus O2 combining to form carbon dioxide and water. All right, not balanced, but it's a redox reaction. And it becomes difficult maybe to see because it's not just an element losing electrons. We can't see the charge necessarily.
Isn't that a combustion reaction?
It is a combustion reaction. So combustion reactions are a type of redox reaction. So because of this, we need to be able to look at a chemical reaction and say, that is a redox reaction. Okay? Because once we know that, then we can determine who's gaining electrons, who's losing, how the process is occurring, and that sort of thing. Now in this one here, we again don't have any good numbers, easy numbers to follow, but we're going to learn how we can look at elements or compounds and find out what the oxidation number of the different compounds or the elements in the compound are. Okay? And these are some rules that we have. Now, the oxidation number is always just the imbalance between the electrons and protons. So if I have an element by itself, like iron, there's an element. How many protons?
Let me look at my periodic table. 26.
26 protons. How many electrons?
Oh, there's no charge, so 26.
Very good. No charge, 26 electrons. So we say then that the oxidation number is 0. And you can write the little oxidation number up there. Okay? So any free element is going to be 0 because there's no imbalance between the protons and electrons. Even if it's something like this, chlorine gas, Cl2, it's all one element by itself. So each chlorine, if it had some sort of oxidation number, then it would show up here in the terms of the charge. And because there's no charge, it means that there's 0 oxidation number. So any free element always has 0 as its oxidation number. In a simple monatomic ion, all right, or in other words, if I have this species, Fe plus 3, then the charge is the oxidation number. All right, so we say that the oxidation number for this iron is plus 3. Even if the iron is combined in a compound, we can say that the charge on this ion, if it were separated, is the oxidation number. Oxidation number here for iron is plus 3, and for each chloride ion is minus 1. So you don't say that the charge for the chloride ion is minus 3 because there's 3 of them. Each one is minus 1. So you want to make sure that you see the charge on the individual atom and not the collection of the atoms. Okay? Another rule, fluorine in its compounds is always minus 1. Group 1 metals, right, they are always plus 1, and that's not surprising because we know that they always form plus 1 when they're in a compound. Group 2 metals also are always plus 2, right? So that's nothing new here, right? We really haven't introduced anything new because essentially what we are saying is that if I have a compound like calcium chloride, I know that the charge on this ion, if it was separated, is plus 2. And so I can say that the calcium has a plus 2 oxidation state as well. And that the charge on each of these chlorines is minus 1. So I can say that the oxidation state on the chlorine is -1. Okay. Now, rule 6, the hydrogen in any compound is a +1. All right, not hard to remember or think about. HCl +1. Cl here would have to be a -1 because that's the charge on it when it dissociates, right? Okay, oxygen. Oxygen is a -2 in all its species. That's, again, nothing hard to remember because we've always seen it want to gain 2 more electrons in its ionic compounds that it forms. Okay? And the sum of all the oxidation numbers of the atoms adds up to the charge on the species. All right? So if I have this compound here, FePO4, and I go Fe3PO4 2, I can know that the sum of all the oxidation numbers, the sum of the iron's oxidation number, the sum of the phosphoruses, and the sum of the oxygens all add up to whatever the charge is on this species. What's the charge on this species, Fred?
I don't know. What's the charge?
Well, there's no charge, right? If there was a charge, it'd be right there.
Oh, yeah, okay. All right, no charge.
Very good. Now, I can use my rules, and I know that this ion here, iron, has what kind of a charge? What kind of a charge does that iron have?
If you use the reverse crisscross, it has a +2.
Very good. +2. And the phosphate?
I'm looking on my chart. It's a -3.
Very good. PO4 3-. So we have a +2 charge and a -3 charge on the different ions there. And so this isn't all by itself, but I can say that my rule number, Rule number 7 says that oxygen should be a -2. And if I take my charges from my irons, right, each one is +2, and I have 3 of them. I have 4 oxygens, 1, 2, 3, 4. And what's the oxidation number on the oxygens?
It's -2.
Yep, that's rule number 7, sorry. -2. And now how many phosphorus, what's the oxidation number of the phosphorus?
I don't know. I don't see the rule on there about phosphorus.
Okay, how many phosphoruses do we have?
Just 2, but you have 8 oxygens.
Oops, I do. I have 8 oxygens. Let me get those in there. 4, 6, 7, 8. And then I have 2 phosphoruses. All right? So the sum of all these oxidation numbers has to add up to 0. Let's see. If I have 1, 2, 3, a +6 from my irons, and a -2 times 8 -16 from my oxygens. Okay? So then that +6 plus the -16 plus whatever my phosphorus is has to equal my charge on my original species, which is 0. So that tells me something, doesn't it? What does that mean each phosphorus has to be?
Well, it has to be 10.
Well, the charge here has to be the sum of the oxidation numbers has to be a +10. But that means on each one here, because there's 2 of them, it had to have been a +5. Okay? So from that sort of deduction there, we can identify that iron has a +2 oxidation state, oxygen has a -2, and phosphorus has a +5. Okay? So again, the sum of all the oxidation numbers in the atoms adds up to the charge on the particle. And the oxidation numbers in group 7 here, fluorine, chlorine, bromine, iodine, is usually -1. All right, so let's use some examples here. One more thing we have to say is that if there's a conflict between any sets of those rules or any of those rules up above, if there's a conflict, then we need to be able to get rid of one of the rules. And we always, if there's a conflict between 2 of these rules, the ones that are lower on the list are the ones that get ignored. Okay? So, here's an example. Can we assign the oxidation states to all these atoms?
I'm not sure what that means.
Well, let's look at our Fe2O3, right? Fe2O3. Our rules, do we have any rules?
Oxygen's -2.
Okay, oxygen is -2. So we can say I have 3 oxygens. All of them are -2. How many irons?
2 irons.
Each iron is what?
Well, I don't know. How do we know?
Well, we knew this, that the sum of all of these numbers has to be what?
I don't know.
It has to be the charge on that species, and there's no charge.
Oh, okay, 0.
That's right, the sum has to be 0. So what does that mean about the irons?
Oh, they have to be +3?
That's right, each one has to be +3. So the answer for this is that the oxidation number on the oxygen is -2, and on the iron is a +3. Now, that's also what the charges on those ions are if you are to dissociate that species, right? That's what the ion would look like. It would look like a +3, and the oxygen would be a -2. So in that way, it's the same thing. And that's also one of the rules, right? Simple monatomic ions have an oxidation number the same as their charge. Okay, so this next one, Na2CO3.
Well, because Na is a +1, does that mean its oxidation number is +1?
That's right. That's right. Very good. So we got the sodium's oxidation number, +1. What about the C and the O?
I don't know what to do.
Well, oxygen was -2, right?
Oh, yeah, okay.
Oxygen was -2. And if we say that we know now that sodium is a +1 and oxygen's a -2, right? Can we, what's the contribution by all the sodiums?
All the sodiums?
Well, yeah, so I have 2 sodium atoms here, right?
Oh, yeah, okay.
And if both have a +1, then that contributes a total of what?
+2?
Very good. And the contribution by the sodium atoms plus the contribution by the carbon plus the contribution by the oxygen atoms, the sum of those has to be what?
Oh, there's no charge, so 0.
Very good. The sum has to be 0. So if each oxygen contributed a -2, how many oxygens are there?
3, so that's -6.
Very good.
So that has to be +4?
+4. Very good. Now, the carbons contribute +4. And how many carbons are there?
Just 1, so it's +4.
Very good. So sodium is +1, oxygen is -2, and each carbon is +4. Okay. Why don't you try that one by yourself? Try these next 2 by yourself, folks at home. Then Fred and I will work on them together. All right, Fred, what do you think? What do we do for this next one here?
What is V?
It's vanadium. Vanadium.
Is it a metal?
It is. It's a transition metal, and this is vanadium 3 hydroxide, right? We can tell because of the hydroxide ion is a -1, so vanadium has a +3 charge.
Well, it's an ionic compound. If vanadium has a +3 charge, then that's its oxidation state.
Very good. So vanadium is a +3. What about oxygen and hydrogen?
Oxygen's a -2. Hydrogen's a +1.
Very good. Now, does that fit our rules?
What rule?
Well, we have to make sure that the sum of all the oxidation number adds up to the charge on the species.
There's no charge on this species, so that's 0.
Okay, so the sum of all the oxidation numbers has to add up to 0 here. How many oxygens?
3 at -2, so it contributes -6.
Very good. And the vanadium?
There was just 1 +3, and then hydrogen contributes, +3, right?
That's right, +3. Each one is +1, and there's 3 of them. So it works out well. So vanadium is +3, oxygen is -2, and hydrogen is +1. Okay. You know the name of this compound?
Is it a polyatomic ion?
Yeah.
Let me look at my chart. Potassium dichromate.
Very good. Potassium dichromate. So, again, if you haven't had a chance to try it at home, try it before we talk about it. What's the oxidation number for the potassium?
Potassium is +1.
Very good. But it says K2 there.
That's all right. Each potassium is +1, so it contributes a +2.
All right, so we say potassium is +1. It contributes a +2. The contribution by the chromiums and the contribution by the oxygens. All right, so 7 oxygens, each one contributes what?
-2, so that's a -14.
Very good. -14 contributed by the oxygens. How about the chromiums?
Can I see those rules again?
Well, yeah, just a second. Let's get her back here. Here we go.
I don't see any rule about chromium.
Yeah, there's no rule about chromium. So we have to do it by deduction again. We have to determine what the sum of all of these should be.
Should be 0, no charge.
Very good.
So chromiums contribute a +12.
That's right. Chromiums contribute a +12. So is the charge on the chromium +12?
Yeah.
Okay, let's take a look. +1 for potassium,
Yeah, that's what we got.
-2 for oxygen. Chromium is +6.
Oh, it's not +12, it's +12, but there's 2 chromiums, so each one must be +6. So that's what it is, +6.
Very good. And we have to recognize that even though +12 was the contribution, +6 is what each chromium has. Okay, fabulous job. Now, here's a tricky one. What's the oxidation number of F in F2O? Why don't you guys try this one at home? Use the rules. Okay, so what were the rules for fluorine?
Fluorine's -1.
Okay, very good. And what's the rules for oxygen?
Oxygen's -2.
Very good. So is that a problem for us?
No, that should be fine.
Well, what is the sum of the oxidation numbers supposed to be?
The charge on this species. So there's no charge, so it's just going to be 0.
All right. Well, if I take the sum of the fluorines and add it to the sum contributed by the oxygen, wouldn't that be 2 of these -2s and 1 of these -2? Wouldn't that be a -4 altogether?
Yeah, there's something wrong.
That's right. There is something wrong. And we can't have both of those rules occurring in this compound. So we have one that is has to be broken. We have to break one of these rules. Which one was higher on the list? The fluorine rule or the oxygen rule?
The fluorine rule.
Okay, so that means we have to concede the oxygen rule. And now we can know that because the sum of this has to be the charge on this species, which is 0, 2 of these -1s, -2, that means each oxygen, or the oxygen here, has to have what charge? Or what oxidation number?
+2?
That's right, it has to have a +2. Okay, so the oxidation number of the fluorines here is -1, and that's not very hard because that's what one of the rules is, but the oxidation number of the oxygen is not -2, it's +2. Okay. How about this? The oxidation number of the phosphorus in H3PO3. All right, so did you try this one at home? Hopefully you did. Tell us, Fred, what do you think?
Well, I think the hydrogen has +1, and there's 3 of them, so that's +3. And the oxygen is -2, and there's 3 of them, so that's -6. And the sum of all 3 of those has to be equal to 0. So the phosphorus has to be a +3.
Okay, very good, a +3. Fabulous job. Okay, how about this one here?
The hydrogen is...
Well, wait, let's give everybody a chance to do it at home first.
Okay.
Okay, now go for it.
Okay, the hydrogen is -2, and the hydrogen is +1, so oxygen's a -2. So the answer is B. I thought one of the rules was that oxygen's -2.
It is, but remember, that when there's two rules that that go against each other?
Do they go against each other here?
Let's see. If hydrogen was +1, right? And there's two of them, that's a total of +2 that's contributed by the hydrogen. And what's contributed by the oxygen, the sum of that has to equal what?
No charge on the particle, so 0.
All right, and there's oxygen, there's two of them. If each one of them is a -2, then it's a total of a -4. See how that doesn't work?
Oh yeah. So which one's higher on the list?
The hydrogen's higher on the list and the oxygen is lower, so this one has to be adjusted. So this is a -2, so each oxygen then is going to be a -1. Okay, very good. Did a great job.
Okay, thanks.